So I'm Nick Pentreath, and today we're going to be talking about deploying machine learning models in practice. A little bit about me. I'm ML Nick on Twitter and GitHub. I'm a principal engineer at IBM, where I work in the Center for Open Source Data and AI Technologies, or CODE. And I work on machine learning and AI. I'm an Apache Spark committer and PMC member. I work a lot on the Spark project. And I've written a fairly out-of-date book now, but on machine learning with Spark. I talk at various conferences and meetups around the world on the topic of machine learning and AI technologies and projects. So a little bit about CODE. When I joined the team, it was known as the Spark Technology Center, founded by IBM to work on Apache Spark and the surrounding data science and machine learning ecosystem. And since then, the mission has really expanded beyond that to encompass the end-to-end enterprise data science and machine learning workflow. So we're a purely open source focused team, and we work to improve enterprise AI in open source. So that includes, of course, Apache Spark as a core component, but also the Python data science stack, and more recently, deep learning frameworks, and a couple of open source projects, the Model Asset Exchange and Fabric for deep learning, which I'll mention a little bit later on, as well as model deployment standards, which we are going to be talking about today. So we'll start with a little bit of an overview about the machine learning workflow, talk about machine learning deployment, what it means, what are some of the challenges, and then talk a little bit about a couple of potential solutions, including container-based and open standards for model serialization and deployment, and then wrap up with a little piece of monitoring and feedback. What happens when you have actually deployed the model, what do you do with it, and wrap up with a summary. So the machine learning workflow, as we all know, it's really easy. Machine learning is simple, right? You take data, you apply machine learning, profit. But in reality, it's a very complex workflow. So we have data, and that is sitting in various data stores. Some of it is historical, some of it is arriving in real time via streaming systems, various formats, various schemas. We have to ingest all of that into our pipeline, and we've got to worry about security, data integrity, regulation, compliance. And then the traditional workflow for data science starts. Data processing, looking at data visualization, exploring the distributions, and then extracting and transforming and engineering features, so turning that raw data into a form that can actually be used in your machine learning model. So there's this piece in the middle of model training is pretty well understood, and that's where data scientists and machine learners would love to spend most of their time, but of course they end up spending 10% of their time, and the rest is this kind of data processing and cleansing phase. And then finally, once you've got a model and you've done your evaluation and your cross-validation and selected the best model, you need to then go and deploy it. And that's what this is really the critical piece, because what comes before is all very important and it's all great, but if you can't do anything with that model, that is all just wasted effort. So really, you need to put it into a live system, predict given new data. You need to make real-time decisions and ultimately decisions that impact business or impact society in some way, impact the real world. And the workflow is actually not just a linear workflow, it's a loop. So once you've got the live system, that system itself creates feedback, and that data that the system acts on that comes back into the beginning phase of this workflow, some of it into your historical data again, or arriving in real time. And it spans teams. So your data engineers might be sitting working on data storage and databases and schemas and all that kind of thing. Data science and researchers are working on the traditional workflow. And then you have a kind of production team, machine learning engineers, who are somewhat spanning this workflow. And in a typical team, you might have multiple personas in the same team, and some of them are going to be straddling different phases. And the workflow or the loop also spans tools. So there's a wide variety of data formats, toolkits, machine learning toolkits, different languages that everyone would like to use. And you need to take all of these into account. And finally, that entire workflow, while critical, is only a small piece of the puzzle. So this is a diagram that I really like from a Google paper, the hidden technical debt in machine learning systems. And it really just illustrates that no matter how sort of sexy and great the machine learning component is, it really has to interface with all the other parts of the system. And in particular, for deployment, it's monitoring and serving infrastructure. So what is machine learning deployment? What are we really talking about here? Well, I like to think of it as the what, the where, and the how. So we don't really worry about the why or the who, because I think those questions are not relevant and you can answer them. But the what is, what are you deploying? What is a model? When we talk about a model, what do we really mean? The where is a combination of the target environment. So of course, are you deploying it on premises or cloud or hybrid or whatever the case may be? But probably more pertinent for our discussion is it batch, is it streaming, is it real time? What format is that kind of prediction going to take? So for our purposes, we're not going to worry too much about batch streaming real time. Everything sort of applies to more or less equally to those scenarios. We'll probably focus slightly more on the real time scenario. And then finally, how are you deploying? This is really the software or DevOps aspect of the deployment idea, right? Are you wrapping up something in a container and deploying it on Kubernetes, whatever the case may be? So the model deployment really encompasses all of these. So we're mostly going to talk about the what. I think that's the most important piece today. A little bit about how, and not really, as I mentioned, much about the where. So what is a model? Most people will think of a model as a logistic regression tree, decision tree-based model, neural network. It's trained to predict given some data, but really that entire pipeline that we talked about and that entire workflow that comes before the model component is also part of that model, right? So you have to transform the data, extract features, do your pre-processing, and that all happens at the training phase. Now, at the prediction phase, these components that come before have to be exactly the same, because if you have any kind of skew between training and prediction time, if you're not applying exactly the same transformations based on the training data to the prediction data, you're going to end up with garbage. So in fact, a model, it's not sufficient just to talk about deploying a machine learning model. You have to deploy the entire pipeline or workflow that comes before it. Data transformation, feature extraction, the machine learning model itself. And one thing that's often overlooked is what happens after the prediction. So many times you have to you might get a probability back, or you might get a class prediction that is an integer, or whatever the case may be. But really often that needs to be interpreted, or it might need to be transformed back into a label and feed into other parts of the system. There might need to be more data attached to that prediction, like confidence intervals, probability distributions, whatever the case may be. So that is also part of it. And technically, even ETL is actually part of this pipeline, because a lot of the time you're going to be dependent on some aggregated data sets that you're extracting features from. And that ETL component, while it's never really talked about as part of the machine learning pipeline, is actually part of that pipeline. So pretty much no framework takes this into account. Even the pipeline, the machine learning frameworks that have pipelines, but really we need to think about this quite carefully to ensure that exactly the same aggregation and kind of ETL steps that occur during our training are available in some form for prediction time. So fortunately for us as practitioners and software developers and data scientists, a lot of this is taken care of in various frameworks that we care about: scikit-learn, Spark ML pipelines, TensorFlow, and R. So these frameworks abstract away some of this concept and allow us to use a nice clean API for constructing pipeline stages and take some of the pain away. Although they're not necessarily complete or perfect. So that's one of the challenges about machine learning deployment, is that the fact that we can't just think about a model, that we have to actually deploy this entire pipeline, which introduces a lot of complexity. But there are many other complexities that we have to worry about. So versioning and lineage, for example. If we need to debug something in production, we need to know where it came from. We need to know which version of the underlying data set, what the schema was, what are the hyperparameters that the model was trained with. We need to be able to go back and trace that lineage, both for debugging production issues or fixing bugs, but also regulatory compliance potentially, as well as security. We have to deal with model size and complexity. So, a typical model might be fairly small and easy to predict with and easy to use and ship around. But when we're talking about very complex deep learning models, recommender systems, we might be dealing with hundreds of millions of users and products in a recommender, or very deep neural network, very complex. So you can very easily get to very complex serving architectures for those models and very large model size. And additionally, you have additional complexities here. A deep learning model might need GPUs, it might need to do batching in its predictions, and so on. Interpretability, really important again for both debugging and regulatory compliance and inspection. We heard about ethics earlier in machine learning. Interpretability is a big part of that. Multi-model serving. In most cases, you don't just deploy a model to production. You want to roll it out in a kind of A/B tested format, or kind of green-blue deployment format. You might want to run various versions of ensemble models, combine them, and you have some of the typical kind of enterprise software requirements of fault tolerance, fallbacks, high availability, what to do if something breaks. You need to be able to keep running in production, keep that model up, or keep at least some way of serving predictions going. So you would have thought that was enough challenges, but we have more. So in addition, we saw that workflow spans teams and tools. We need to bridge that gap. So as we take a model to production, we need to bridge that gap between various languages, frameworks, versions, dependencies, and we need to do that in a kind of unified manner. And performance can really vary significantly across these dimensions. So a model in production that was developed using R or or Python in some cases might be really slow. And production team might want to rewrite that thing in Scala or Java, C, whatever the case may be. In some cases, Python might be fast if it's calling into NumPy, or if it's calling into TensorFlow, PyTorch, or so on. But we don't have a lot of visibility necessarily into those performance characteristics. We then have an organizational challenge, which is this friction between teams. So the data scientist and the researcher always wants to use the latest, greatest framework and model. They might want to be pushing a model out based on the master branch or an RC branch of TensorFlow because it's got some new operator or some new neural network layer. Production doesn't want that, right? They don't want to be serving something off a bleeding edge development branch, right? They want stability, they want control, they want to minimize changes, and they don't want to be woken up at 3 in the morning, with a burning production serving cluster. And business doesn't care that you're using TensorFlow or that you're running on Kubernetes. Okay, they care about business metrics. They care that it's always up because then the product must always be working, and they care about the impact of that model. So the proliferation of formats is another issue. As you need to bridge the gaps between all these different frameworks and languages and runtimes, each of them has their own way of doing things. Each of them has their own format. Some of them are open source, open standards, and we'll talk about some today. Some of them are open source but non-standard. So they're custom, although that you can go and check them out and understand how they work. And then, of course, you may have proprietary formats for proprietary products, and then you have no portability and you're locked in. So it may work, but that you have issues there. So invariably, this lack of standardization leads to custom solutions. So every single deployment, every single framework that you develop internally ends up being custom, or at least having significant custom components. And sadly, where standards do exist, as we will see a little bit of, you end up needing to customize via sort of custom extensions, or you need to extend the standard in some way, and you lose all the benefits of standardization anyway. So there are many challenges. On the pure deployment side, one of these solutions is containers. We all love containers. So container-based deployment does have significant advantages, and this goes for most software deployment. It's not specific to machine learning necessarily. So you have repeatabilities of configurations, the ability to have your data scientist know that, and production know that what runs on their laptop or on the kind of research cluster will run in the production serving layer in the same way. So what's important there is a separation of concerns. It allows you, as a data scientist, researcher, machine learning engineer, to really focus on that what component, right, and not really care about how. That can truly be left up to to production team and the DevOps team. So it also allows the data scientists to use the language or framework of their choice, so they feel comfortable. And you get a couple of things for free. Let's say if you're using Kubernetes or something similar, like you get monitoring and fault tolerance, high availability, and some of these things, not necessarily machine learning specific, but on the kind of general deployment side. But in my view, containers are great, but what goes into the container is the most important thing. So you can take whatever scikit-learn model you have, TensorFlow model, whatever the case may be, pipeline, wrap it up in a container, and away you go. Deploy it, right? Problem solved. But recall that the performance can be variable across all of these dimensions. So how do you know that when that container gets pushed to production, that your SLAs and your response time and your latency is going to work, right? If you're changing versions, so container-based deployment helps you manage versions because you don't have to worry necessarily about what version is running, and you don't have to match the version of your serving framework with the underlying producer. So match versions of Spark or TensorFlow or scikit-learn. But you don't know if a new version that the data scientist wraps up in the container on that master branch of TensorFlow is suddenly going to hit an edge case. Or performance degradation, right? So you have this level of uncertainty, and you can't guarantee performance. So it requires DevOps knowledge, deployment pipelines, good practices. That's not a bad thing, but it's just it's an investment that needs to be made, right? So it's not as simple as just saying, well, let the data scientist deploy from his laptop. In reality, you need proper testing, proper CI, proper validation before things go into production. So you need a big investment in those pipelines. And this does not solve the issue of standardization. So again, if you just wrap up some sort of ad hoc scikit-learn model, you're not standardizing on the format of the API that is exposed. So it's no good that you just the data scientists can do what they want. How does the rest of the system and the rest of the business interface with that model? You need some form of standardized API that is exposed so that users of that model, internal users, external users, can actually know, how do I use it? How do I call it? What does it do? So invariably, you need some form of serving framework that sits on top of that. So I'm going to talk a little bit about the model asset exchange that our team has recently released, and it's still in its infancy, so it's very, very young and very new. But MAX, as we call it, is a one-stop exchange to find machine learning, deep learning models, and to try and lower the barriers to entry to obtaining, training, and deploying them. And we try to use a standardized approach for this. So for the training part, we use the Fabric for Deep Learning, which is an open source Kubernetes-based deep learning training framework, and I'll mention it again at the end. But really what I'll talk about now is the inferencing. And this is, in the first version, very simple. And all we really want to do is take a containerized approach. So, initially just really running on Docker, but of course, once it's in a container, you can look at running it on some container service, Kubernetes, etc. And then deployment simply becomes, deploy the container, expose the API ports, and then we develop a lightweight REST API wrapper and try to make it standardized and generic. So wrap the back-end models, whether it's TensorFlow, Keras, PyTorch, in a generic wrapper that exposes a kind of prediction API. So the API, the REST API level of the framework doesn't really know anything about whether it's a Keras model or a PyTorch model. It just can call into a generic API. And then we use Swagger to expose an API documentation. So that Swagger definition allows you to auto-generate some nice user documentations that developers can come and play with it. But it also has some really nice properties, which means you can, using that Swagger definition, auto-generate client code. So all of this, is a step towards this kind of standardized mechanism and exposing a standardized prediction API so that the rest of the business can come and use this. So as I mentioned, it's really early days. We're trying to grow this as a kind of open exchange, and this is really just a first cut of what a standardized sort of serving API might look like. But there's some really interesting projects, some of which we are evaluating to use that are trying to do this in a kind of more generic way. So these are container-based serving frameworks. There are probably more that I might have missed, but these are two really interesting ones. The first is Selden Core, which runs on Kubernetes, and it does pretty much what I showed for Max. Each model is its own sort of container, but it tries to expose a shared and common API layer that each model and kind of component will expose. And Clipper is a UC Berkeley Rise Lab project, which I don't think it runs on Kubernetes to my knowledge, but it has the same kind of core concept, which is that each model is wrapped up as a Docker container and kind of isolated, and then there's a serving layer on top, which aims to expose a common API. So really, this is trying to abstract away what is the framework that is underlying the model, how exactly does it work. All the user of the high-level serving framework cares about is what data do I need to pass into this model, whether it's exposed as gRPC or REST API, whatever it is, it doesn't really matter, and what do I get back. So what does it do? What is the input and output, right? And then on top of that, they're looking to support these meta algorithms, ensembles, A/B testing, bandit algorithms, and so on. Okay, so we've seen a little bit about the how, potentially the how of model deployment, and we'll talk now about the what. So open standards is something I believe in a lot, and really, I think the best solution to trying to bridge that gap between frameworks and languages and teams is to try and standardize on a model serialization format, so that we can, link up all these different frameworks and bridge that gap. So no matter what, producer you're using in terms of, the machine learning framework, you can export to the same standardized format, and then your serving layer can just read one format, and all it has to worry about is one thing. So probably the earliest and most widely used currently and widely supported currently standard is the probabilistic model markup language, PMML. And this was created by the Data Mining Group, which is a kind of industry consortium. And it's an XML-based format that specifies certain built-in operators and built-in models. So it works really well for some of the traditional machine learning models, like obviously regressions and linear models and tree-based models, and the sort of typical transformations that come before, categorical indexing, on-hot encoding, and so on. There's wide support, good support for Spark, scikit-learn, R, XGBoost, LightGBM, so all your favorite kind of machine learning models and frameworks. But there are a couple of issues with PMML. And one is that if what you want to do fits into what the standard offers, it works very well. But if you want to do anything that doesn't quite fit into it or represents some sort of arbitrary analytic application or program or transform, it breaks down. So what ends up happening is that people develop custom plugins for their particular use case, and then that has to be done in the serving layer or the execution engine as well, and you completely lose the standardization, right? Because you've got a custom component which is not shared across the standard. It means that you have zero portability outside of your organization. One of the other sort of frameworks out there, it's not so much, it's an open format, but not a standard, is MLeap. And MLeap was really born out of a frustration with Spark. And that is all, could probably be a whole other talk, but Spark ML has a couple of serious shortcomings, and one of them is that in order to score a model with Spark, you have to use the Spark SQL runtime. So you have this tight coupling between training your model on Spark and having to serve it on Spark. Now, for certain scenarios like batch scoring or streaming, that works pretty well. But for real time, you end up with it being really slow. So what a startup called Combust.ml did is they created MLeap. And pretty much what they did is copied and pasted most of the kind of execution piece of Spark ML code, and then created their own open format, but their own interchange format in JSON, and sort of created a local version of a Spark data frame. So it all works, and it covers all the Spark ML components. They've added some scikit-learn and TensorFlow. It's a really great initiative, and it is very performant. But as there's a couple of pretty serious shortcomings in my view, and probably the biggest one is that it forces this tight coupling between the model producer and the consumer. So as you change versions of Spark, for example, you have to keep upgrading your execution side, right? So you have to move in lockstep, and if you're using MLeap for serving, you have to upgrade that version. Or the alternative is that each new version of MLeap has to be completely backward compatible with every single previous version of Spark. And that leads to a lot of complexity in the execution engine. So this may or may not be a downside, but you have to implement custom components in Scala. So for many people in machine learning may not use Scala, so you have to then learn Scala to export your custom scikit-learn or neural network model into MLeap. So TensorFlow serving is not so much a format or a standard. It's really the saved model format is the format part of it. But that exposes some standardized APIs for classification, regression, and prediction. So it works really well for TensorFlow and for serving TensorFlow graphs. But to be honest, it's quite difficult to use if what you want to do is not expressible in TensorFlow graphs. So it does support this kind of arbitrary servable concept where you can just implement an API, but as far as I know, that has to be done in C++, which may be quite a big barrier to entry. So because it really supports TensorFlow graphs, if you have a pipeline that uses some transformations that cannot be expressed in that graph, then you basically can't use TF serving. So what is one way of kind of trying to generalize this neural network graph concept is the Open Neural Network Exchange. This was introduced by Facebook and kind of championed by Microsoft as well. And Facebook had, was using PyTorch for a lot of research and Caffe for serving on their neural network models. And they wanted to bridge that gap and really create an interchange format that they could take, from PyTorch into Caffe for serving. And it's become, a lot more widely used. So it's a standard for serializing, the computation graph, and it is neural network and deep learning focused, but it's not limited to that. So what's really useful and interesting is that the serialized graph is self-describing. So you can take that protocol buffer file, and that fully describes both the weights and parameters of your model, as well as the actual transformations that occur in the graph. So that it's a completely portable little piece of of serialized model, and as long as you have a compliant ONNX engine, doesn't matter where that protocol buffer came from, what produced it, you could actually serve it. The downside is that it doesn't have a lot of support for your traditional machine learning, so your tree-based models and the typical transforms that would come in your machine learning pipeline are not really expressible at the moment, though I know that is being worked on. Okay, so something that I'm really interested in particular for the traditional machine learning side, is the portable format for analytics, PFA. Now this is being championed again by the data mining group, and we recall that DMG created the PMML standard, but it has many limitations. And PFA was created specifically to address these shortcomings. So PFA is a JSON serialization format where the schemas and types for inputs and outputs and functions and so on are all specified as Avro. So you can pretty much encode whatever type you want. And it encodes the functions called actions in PFA that are applied to the input to create an output. And it's got a couple of other language constructs to make it what is essentially a mini functional math language plus a schema definition. And because it's got this type system, you can actually take a valid PFA document and statically verify that it will work at effectively kind of compile time. So you don't have to worry about runtime sort of type errors, incompatible types between functions and inputs and outputs. So this really gives you, in a very similar way to ONNX for the deep learning side, it gives you this true portability across languages, frameworks, runtimes, versions, and it cleanly separates the model producer from the model consumer. So a little example about how this works. If we take a multinomial multi-class logistic regression, we can see that the PFA document, which is the kind of serialized model, specifies an input and an output type. So in this case, an input would be a vector, output would be a class prediction, and you specify the action using, in this case, a few built-in functions. And it looks very natural. I mean, despite the fact that the JSON is really not meant to, not good for human readability, it's really for machines to manipulate. We can still see that we apply a linear regression model, effectively a dot product, between our input vector and this model. And I'll talk about the cell in a minute. Then we apply a softmax and then an argmax, and away we go. So it looks very similar to the math behind the prediction. So we saw there a reference to a cell, and this is how PFA manages state. So a cell is really a kind of named value that is a type of global variable, and its type is specified again by Avro. And the key here is that cell values can be mutable within an action. So you can, while you are in that prediction action being executed, you can update or change a cell, but they're immutable between actions. So this is typically where you would store, things like model coefficients, your mappings in vocabularies, the min and the max in your scalars, or the mean and standard deviation, whatever the case may be. So we can see here, if we are extracting from a set of text, or turning a set of text into term vector, we might have a vocabulary which is basically a hash map of strings to integers, and we define a cell that looks like that. There's also something called pools, which is really a cell with persistent storage. So you can think of it as more of a database that is persistent across actions and across PFA engines. So it's kind of like a global shared state. And some other features that I mentioned, because it aims to be a mini sort of language in a way, we have control structure, scoping, user-defined functions, including anonymous functions or lambdas, casts, null checks, and some sort of basic logging and kind of exception handling. But a very comprehensive built-in function library that encompasses math strings, array processing, maps, statistics, all the kind of things that you kind of need in your typical machine learning pipeline of transformations. So I'll mention a library that I've been working on called Aardpfark, and this is for PFA export to Spark ML pipelines. So this is again trying to address that issue that we heard about earlier with Spark ML models. And the reason, so that's the main reason that we started with Spark, because there's this pressing need within Spark, but we hope to extend it to others, to other frameworks. So I'm from South Africa, and for those of you that don't know, which is probably everybody, an Aardvark is literally in Afrikaans an earth pig, so it's an anteater, and it goes around, eats ants. So Aardpfark is the name playing on that. And really, all this is a DSL in Scala for creating PFA documents, and then using it, we use that DSL to export Spark ML components. So if we compare what we had before the logistic regression, this is how it looks in Aardvark. We define a PFA document with input and outputs. We use Avref-OS, which does some really nice macro stuff in the background, which I don't get involved with or really care to understand too much. But we get some nice automatic schema inference, and then we create an expression here, which will then generate exactly the same JSON that we saw before. So in terms of coverage, we have pretty much all the predictors in or machine learning true models in Spark. Most of the feature transformers, support for arbitrary pipelines, and a growing set of equivalence tests between Spark and PFA. I'm not going to actually talk about too much about the challenges, but suffice it to say that Spark creates some issues that make it more difficult than it should be to do PFA export or any kind of export to a non-standard format. But what is worth highlighting here is that Spark can operate on generic vectors. So you can have a data frame that passes in a sparse or dense vector, and Spark knows how to handle that. And that is not supported in PFA, so that's a big downside and a missing feature that we would like to work on in the actual standard, and that makes things pretty painful at the moment. But that can certainly be solved without too much difficulty. It just needs to be added to the standard itself. So PFA provides this open standard, an open source and open standard, true portability across languages, frameworks, runtimes, and it really separates the concerns and has a clean separation between any kind of model producer and the model consumer or execution engine. It solves a significant pain point in the Spark ML community and certainly the wider ML community. And in the future, we'd like to look at releasing Aardvark as open source. That'll take a little bit of your internal process to work through, but that's the aim. And then later add support for other frameworks. And I mentioned a couple of improvements to PFA that we'd like to propose, the most important being this generic vector support. Okay, so the final thing, we've talked a little bit about potential solutions to how to deploy models, but really, once you deploy the model, that is, what do you actually do with it, right? It's not sufficient to just have the model in production making predictions. You need to do monitoring, and this encompasses both traditional software monitoring, so things like latency, throughput, uptime, anything like that, with machine learning specific monitoring. So we would like to monitor metrics, accuracy, what is happening with this model's performance over time, and can we capture model drift or a data distribution drift between what the data is trained on and the data it's seeing for prediction. And then we need to combine that with business metrics. So even though our model might be predicting sort of fine, the model performance versus the business metric that we care about, that relationship might actually change over time. So we need to keep a close eye on that. And of course, retrain models if any of these things degrade. And then finally, a model doesn't exist in complete isolation. It is interacting with the world around it. So, the feedback that comes from a model, or the prediction that comes from a model, in many cases actually influences the behavior of a user. So, in recommender services, bots, AI assistants, this is a huge issue to be aware of, is that your system and your model is actually influencing user behavior by making recommendations. So we have to be aware of filter bubbles, bias, and these kind of things that can sneak in here. So I believe that we have to have some level of humans in the loop. We obviously, combined with monitoring, we need to know and guard against these kind of potential pitfalls that come from feedback loops. Okay, so I'm sure you all feel like this dog. I know I do. So in conclusion, a few points to make. Deployment is about deploying pipelines, not just machine learning models. So we need to deploy the entire workflow that we saw in the beginning, not just our latest, greatest neural network. Containers are great, but they are not sufficient. So what matters is what goes in the container, and how you stack these containers up to create something that is really useful and interesting. Embrace open standards and formats. I truly believe in them. There certainly are downsides to them, but I believe the benefits far outweigh those downsides. And deployment is really the beginning, not the end. Once that model is out there, it's the beginning of the road. We have to obviously monitor it and see what it's doing in production, see how it's influencing the world, but really have to move to continuous learning, continuous retraining, and that is the hallmark of an intelligent system. It's one that has this continuity about it, where once you push that deploy button, it's really the start of that whole new process, and that is a completely open open sky at the moment. I think we're still trying to solve the earlier problems, and we haven't really gotten that much to this kind of continuous learning problem. So that's going to come in the future. Okay, so thanks very much. I mentioned Coday, so coday.org is the link, and I encourage you to go check it out. I talked about Max, and you can find the link there to the Model Asset Exchange. The Fabric for Deep Learning, or FIDDLE, is a framework-agnostic, Kubernetes-based deep learning training system. It runs on a Kubernetes cluster and supports TensorFlow, Keras, PyTorch, Caffe, whatever your favorite framework is. So that's recently open sourced by IBM Research, and it actually forms the core of our Watson Studio deep learning as a service. So we're really kind of backing our commercial offerings with open source releases. So I'd encourage you to go check out Watson Studio. We really have aimed in this kind of cloud product to solve many of these deployment issues and this end-to-end machine learning challenge. And you can follow me on various social media. Obrigado. So I think we've got time for some questions.
Perguntas, pessoal.
Hi, thank you very much for the talk. Machine learning deployment is very underrated in the community. Most people don't worry about it, but that's when you get the real value out of the system. So my question is, how do you handle automatic retraining? Should you do it, and when?
Yeah, very good question. In my previous life, before IBM, I built a startup that created a recommendation engine as a service. So we had this exact problem, right? Customers have to have their models retrained periodically, and how do you make that decision? So the ideal is, of course, that we would like to automatically retrain and do it based on some reasonable trigger. But the reality is that is very difficult. Right? So It's costly in terms of engineering resources, potentially costly in terms of compute resources, and how do you know when to retrain in that automatic system? So what we ended up doing, which is probably what many people end up doing, especially in a smaller organization, is you just sort of do a thumb suck and say, okay, well, I'll probably do it every day or every week, and maybe adjust that based on the size of the data set or how often it is changing. So that's probably the reality, right? The theory and the goal should certainly be to say, well, if we can accurately track machine learning metrics around the model and understand, is performance degrading? Well, certainly if performance is degrading, or if we're uncovering some critical issue in our monitoring, we definitely need to retrain, and that's more of a reactive, kind of try and save performance or save cost or save face or whatever the case may be. But then there needs to be another aspect to it, which is as new data is coming in, we need to make a decision about if we are retraining that model or updating it, how is performance changing? So, I mean, this is an unsolved sort of question, but the idea would be, to try and automatically run our candidate models as new data arrives, and sort of understand if we are above a threshold for performance increase, we'd like to deploy that new model. But otherwise, it's probably not worth taking the risk, because if we're only getting an incremental performance gain, it may not be worth it. So yeah, I mean, this is an open question. The big consumer internet companies are doing this kind of thing, but for many, it comes down to a cost-benefit trade-off, right? And I think in reality, you end up doing it fairly ad hoc.
You mentioned Seldon as one of the platforms that are gaining traction. Are you aware of any large deployments in production of Seldon?
I don't know the Seldon folks very well, so I'm not aware of anything major in production. It just seems that from the open source side of things in the community, it seems to be gaining quite a bit of traction. But it's still new, it's still young, so adoption will take time to grow, and it's not it's not proven yet whether the way that they have structured their kind of